Good morning. Today we're going to be looking at kinematics. We have already looked at scalars and vectors, but let's just quickly review these. A scalar is a number without any direction associated with them. A couple examples would be time, temperature, or distance. Scalars are added just like any regular number. If a person walks 5 kilometers and then 4 kilometers, the total distance walked is 9 kilometers. Unlike vectors, vectors are numbers that have both a size, which we would call a magnitude, as well as a direction. So for example, you might have traveled 0.5 kilometers east. Vectors cannot be added like regular numbers. The direction must be accounted for. To add vectors, a process called vector addition is used. When stating the answer for a vector, a direction must be given. What vector addition is the process of finding the sum of different vectors. This is done most simply by just drawing the arrows to represent each vector. When adding multiple vectors, the arrows should be aligned tip to tail. This is the most important piece of the vector addition. You have the tail end of the vector represented over here. You have the tip represented on this side as well. If you have two vectors, so again, imagine that we're moving towards the east over here. Vector 1 is going to be here, and where you begin the next one, the next vector is at the tip of the first vector, connecting it with the tail of the next one. And so the resultant vector, and that's what you would call when you add two vectors up, would be from the initial starting point to the final point of the second vector. And if there was 3 vectors you added up, it would be at the final point of the third vector. And so you go from the starting point, the tail, to the very tip of the very last one that you added. And that would be your resultant vector, which happens to be the next definition here. Resultant vector, which I normally just call it VR, and that's the subscript R, is the answer and points from the beginning to the end of the chain of vectors. So the beginning all the way to the end. So the resultant vector for here would be from this point all the way to the end. And again, it would be a straight line to the right. Here are a couple examples. Add 3.0 meters south and 5.0 meters south. For the first couple, we luckily will not need a ruler, but if you do have a ruler or access to one, you are going to need one for an upcoming couple examples here. So just be aware of that. This first one right over here, if you go 3 meters south, followed by 5. And so again, I try my best to be representative. If this is approximately 3 meters, this is approximately 5 meters. When you're just drawing it out where it doesn't need to be exact, then a nice little representation is fine. We're going to be drawing some examples where it actually does matter, and you need to represent this properly. And so we'll be getting to that soon enough. So if you add these two together, your resultant vector is going to be from the starting point, the tail, to the very tip over here. And so what you end up getting is 8 meters south. For the next one, we have 3 meters west, followed by 6 meters west, and then 4 meters east. So if we start over here and we go 3 meters to the west, followed by 6 meters to the west, twice as long, approximately, and then 4 meters east. And as you can see, every time I'm adding it, it's always tip to tail. So tip of the previous to the tail of the next one. And so these technically are touching like that. And then lastly, 4 meters east. So again, tip of this one to the tail of the next one. And the next one's going to be 4, so it's going to bring us to about there. 4 meters to the east. So you've gone a total of 9 meters to the west, 4 meters to the east. And so when you're drawing your resultant vector, again, it's going to be from the starting point. And I'm just going to draw it below here just so you can visually see. It should be drawn right over here, right where the tail is of the first one. But I'll just draw it below just so you can see. So the tail of the very first vector to the tip of the last one. That's what you're looking at. So it's going to be 5 meters west. And that will be your resultant vector right there. Unfortunately, or fortunately, not all vectors are going to be just straight lines, either up or down, uh, or in this case, left and right, or east and west. Vector addition can also be performed for vectors that are more complicated, and that's what we'll be looking at. Vectors with angles cannot just be added like other vectors. You just can't go like we did in the past example, 3 plus 5, or in this case, 3 plus 6, and then minus 4. It's more complicated. And we'll be looking at two separate examples that can be used to solve vector addition problems. So the first example is going to be vector addition with scale diagrams. And this is where you're going to need to have a ruler if you're going to properly do this. Unfortunately, I actually didn't even bring a ruler home. I thought I had. So I'm going to just use my answer key when we get to this portion here. But I'll walk you through it. Vector addition problems with angles can be solved using a scale diagram. This involves drawing an accurate representation of the vectors and measuring the resultant vector, which would be the answer. You will need also a protractor to properly measure the angles for this as well. And so you might not be able to draw these out precisely today when you watch the video, but in the future you're going to need to make sure to have a ruler and a protractor with you when drawing specifically the vector addition with scale diagrams. So what are the steps involved here? Well, first you have to choose a scale for the diagram, and the vectors should be able to fit easily on the page. Determine the scale length for each vector, then draw them tip to tail, add them up. Be sure to measure the correct angles and scale lengths. Finally, draw the resultant vectors from the beginning of the vector chain to the very end. And then measure that scale length, and you need to also then change it back into the actual value using your scale that you had determined before. And then lastly, most important, well, not most importantly, but part of it is you also need your angle. And I say most important just because a lot of the time people forget to include the angle when expressing their resultant vector. And remember, vectors need both the length over here as well as the angle, which would be your direction. So do not forget that as well. So our example below is if you add 200 meters north and then 300 meters 30 degrees northeast using a scale diagram. And let us express this in a little bit of a different way. If yours isn't changed, let's change this to represent how I wanted it to be. So sorry about that. 30 degrees north of east. And so that's what it should be. Maybe you should draw this up above too, just so you're gonna have enough room in this area here. You probably want to choose your scale right. I chose a silly scale. I chose mine to be 1 inch equaling 100 meters. In reality, I probably should have done maybe like 1 centimeter equaling 100 meters. And so what you end up getting is the following. We have a diagram here, and so as you can see, it extends into the next question here. And so I started right over here at this point, and then I measured 2 inches directly north. And so remember, I had set my scale to be 1 inch equaling 100 meters. That was my scale. So I started here, I measured 2 inches up, at which point I went 30 degrees north of east. So if you're going directly east, you're going to be looking at a 30-degree angle above that. So it's 30 degrees north of east. And so you're going to take your protractor right over here. Maybe it's not even a bad idea to have a reference point, the horizontal line right over here. You measure that 30-degree angle. And at this point, then I drew 3 inches in that direction right over there. And ultimately what happens, how do you add them up? You start at the beginning, so the tail of the very beginning to the tip of the very end. And so this is your resultant vector right over here. Once I got my resultant vector, I did 2 things. Number 1, I measured this length and I got 4.81 inches. And then I used the scale of 1 inch equaling 100 meters to make it 481.3 meters. And if we wanted to express it exactly like 41.3, I guess I could have had an extra 2 sig figs there. Maybe we should have just put 30.0 like that. We could do it like that. And then have this 36. I don't know what this ended up rounding up to. This is very difficult to have anything more precise than this, especially on your protractor. So to the nearest degree, I would say is completely acceptable for this. And so even if we did include the 4, that's fine. So once we converted the inches back into our correct measurement here, the next thing we did was I measured this angle right over here. And it measured to 36 degrees. And then afterwards, I then determined, well, what's the reference point? 36 degrees by itself is just not good enough. You need to actually express it based on like north, east, south, and west. And so I decided to go and use this reference point right over here. This is already going directly north. And so I said, well, it's just 36 degrees east of north. And that's what I ended up writing over here. And so you could have expressed that a little bit differently. You could have had another horizontal line right over here and then calculated 90 minus this 36 and had a value 54 degrees north of east, which also would have been a correct way to express that. But this is your resultant vector right over here. For the next example, if we took a closer look at this, I believe this time I ended up saying, well, 1 centimeter equals 1 kilometer. 1 centimeter equals 1 kilometer. This time I was able to fit this onto the page a little bit nicer, and there's 2 different vectors here. So there's one vector that's 21 degrees north of east for 50 kilometers. So in reference over here, that's going to be 5 centimeters. And then, as you can see, one of the things I do too is I always, often I draw my horizontal line right over here, or vertical line, as you'll see in the next one. So just like this one over here, how else are you going to properly draw this angle right here? So I started with my horizontal line. I measured 21 degrees above that, and at that point I just had a little reference point there. It's hard to see that little extra dot over here, but I just put that reference point down so that when I did my measurement, I could figure out it would stay in line. It would be exactly 21 degrees. At which point, so tip to tail, so the next vector starts over here, the tail does to the tip. And again, this time I drew another horizontal line up here just for reference point, as well as the vertical line. This one here was 30 degrees, I guess, east of south. And so I ended up drawing that 30 degrees east of south and tip to tail. And then the resultant vector is this dashed line. So it starts from the beginning and goes to the very tip of the final one there. And measured it again. It came out to about 7 centimeters. So I converted it using my scale factor here, 1 centimeter being 1 kilometer. So that was approximately 70 kilometers. And lastly, you always need your angle. So I went back to this reference point right over here, the horizontal line, and then I measured this small angle right over here to be 14 degrees. And so then that was 14 degrees south of east. So it was east, and then it's 14 degrees south of east. So this would be our final answer right over here. And again, I'm not like super worried about the significant figures specifically with these, just because it becomes a little bit tricky and difficult to express when you're using a ruler and then you're only able to be accurate to the nearest like 1/10 of a centimeter. And so based on these values right over here, how accurate and precise is it? It's not going to be as precise as you would get if you were to actually do the calculations, which is going to be the second method to calculating vector addition. But this gets us pretty close. I'm not going to lie. It's going to get us pretty close to the exact answer there. So that is the beginning of scale diagram vector addition. Now, the second way, and this is where we're going to get to work the majority of this year, but again, it's useful to know both ways. And this way is the vector addition with components, where you're breaking everything down into your x and y components. When adding vectors, the path the vectors take really doesn't matter. So just like 4 plus 3 or 3 plus 4 both get you to 7, it doesn't really matter which one you add first. The same is true with vectors. It doesn't matter on the previous example there, had we added the other vectors first. So had we taken this vector right over here and added this one first, followed by the vertical 200 meters north, if we'd gone this plus the next part right there, our final value would be from this starting point up like that, And that's going to be exactly kind of what we're seeing this resultant vector. It would just be parallel. It would be over here. It would be the same length. It would be the same angle. It would just have been done the opposite way. So 200 plus 300, 300 plus 200. It doesn't matter with the vector addition. The order doesn't matter. So you can choose one or the other to be first. Components are vectors that are parallel to either the x or the y-axis of the grid and can be used to create a new path for a vector. They are called the x component and the y component. They create a right triangle from the original vector with the original vector as a hypotenuse side of the triangle. And so this might sound a little bit difficult or to follow through, but trust me, once we break this down, it's not going to be too difficult. When using the component method, trig ratios will need to be used to determine the magnitude of both the x and the y components. So very useful to remember the SOHCAHTOA, and that's why we kind of reviewed it a little bit before as well. So if we have a vector here, it's 7 meters, 22 degrees north of east. That's what we have right over here. If we were to break it into the x and y components, this is kind of what it would look like. We would have our x component right over here. And we're going to need this value right here, the x component, and then later on we'll get the y. So if we're looking at the x component, that's the adjacent side over the hypotenuse, we're going to be using cosine. And so we'll write it out fully. Cos of that particular angle, 22, is equal to the adjacent side over the hypotenuse. And at this point here, to get rid of the 7, you just multiply it by 7 on both sides. And again, I'm going to write with the variable being on the left-hand side. So it might look like I'm skipping a step here. I'm just switching the fraction to be on the left side and then multiplying both sides by 7. So it's going to be 7 cos 22 degrees. And more often than not, you're going to almost skip this step over here at some point to starting to write just this as time goes along. You punch it in on your calculator and we're going to have 6.5 meters. Now for our y components, and I say plural here, but it's just one y component this time. It's going to be opposite over hypotenuse. So we're going to have the trig function sine, opposite, adjacent over hypotenuse, opposite over adjacent. What is this? Opposite over adjacent, didn't notice that before. And yeah, that's a pretty ugly looking U there. All right, make sure to change that. I can't believe I didn't notice that or nobody ever called me out on that. All right, that's sine theta right over there. Perfect, opposite over hypotenuse, yikes. Sine 22 degrees is equal to y over 7. Look at how these are very, very similar here. And so we're gonna do the same little trick there, bring the variable we're trying to solve for on the left, multiply both sides by 7, and we're going to get 7 sine 22 degrees, which is equal to 2.6 meters. And when expressing these two values, especially when you're dealing with vectors, you need to determine, is it positive or negative? So we are going to be saying anything to the right is positive, anything up is positive. And so this is going to give us a positive value. The y component is also positive. It's to the right, it's also up. It's very important to begin to do this because as we draw things to the left or down, we're going to have negative components for those pieces. So what do we have here? To follow steps when using the vector addition, make sure that we're using SOHCAHTOA, not SOA, it's SOH. SOHCAHTOA, be sure to label the directions. And so again, with those directions right there, it really says it within that positive or negative. So it's positive in this case, positive over here. And so on. Calculate your x and y components. Good. Add or subtract the vectors in the x direction. So this is when we're doing multiple components, right? So multiple vectors. Right here in this previous example here, we had only one vector. So how in the world can you calculate the x and y components, plural? Well, it's if you have two of these vectors, you would do both breakdowns for the x and the y components, and then you would combine the x components, combine the y components, and then at that point you would redraw the x and y components, connect them tip to tail, and then calculate your resultant vector. And I believe it probably says that here. Add or subtract x, so combine the x's, combine the y's, create a new right triangle Very important. This is where some people forget this step, and it's a critical step, with the numbers found in steps 3 and 4, and then calculate the hypotenuse. So the hypotenuse is your resultant vector. And then also the angle. So again, that's something that people will sometimes forget. So don't forget both. The length of your hypotenuse of this new triangle as well as the angle. And you'll need to include both of those in your final answer. So let's go ahead and add these 3 vectors up. So what we have in front of us is 3 newtons north, 5 newtons east, and 2 newtons 30 degrees south of east. And so we are going to be breaking it into the x and y components and then adding them up. So that's using components here. So if we say, what are our x components here? And one of the things I want to do too to make this a little bit simpler is I'm going to be labeling all of these. So this is going to be vector 1, this will be vector 2, and this will be vector 3. So if we're looking at vector 1, there are no x components for vector 1, and so we will just not include anything. It's only going up. The next one is and does have an x component. It's actually the entire thing of it. And then this one has a component, an x component, so it has both a y component and an x component. So you could call this v3 x, we call that v3, we could call this v3y, and so our v3 vector is this one, broken into components. This is the x, that is the y. So we said, what are all the x components? Well, we're going to have vector 2x as well as vector 3x. And now if we want to determine what each of these is, we already know what v2x is because v2x is just v2. But we do need to calculate what vector 3 in the x component is. So let's do that first before we go ahead and add these two up. So we already know that vector 2, the x component, is 5 newtons. But vector 3x, what is this going to be? This is going to be your adjacent over your hypotenuse. Your adjacent over your hypotenuse. And remember on the previous example, we just multiplied the value, the hypotenuse, by cos 30. So if we flip back over here, we had our x component here, we had the hypotenuse that we did know, and what we ended up having was the unknown value was equal to the hypotenuse multiplied by the trig ratio times 22. So 7 cos 22. So hypotenuse, trig ratio, angle. Hypotenuse, trig ratio, angle. So if we had the hypotenuse 2, trig ratio is the cos 30. So it would look like 2 cos 30. And again, if you need that to be broken down into what it was before, you could write that down. So what does that look like? I'm just skipping this one step, so I'll just show you up here quickly. But I don't want to have to do that over and over again, so I am skipping that one step. What that one step was this. Cos of 30 degrees is equal to your adjacent side, which is your x component of your third vector, over your hypotenuse. And then we just multiply both sides by 2, bringing the 2 over there. 2 cos 30 equals v3x. 2 cos 30 equals v3x. Now that we know the second vector's x component, our third vector's x component, well, we just have to punch this in. We almost know it. Once we punch it in, we get 1.73. Now we can add these two values up. So it's going to be 5 plus 1.73. And let's just confirm positive, negative values. It was to the right, so that was a positive value. We should have probably just checked that before. This was also to the right, so this would have been a positive value. So it's actually a positive value plus another positive value, giving us a larger positive value. So representing, it's going 6.73 newtons to the right. After our x components, let's do our y components. And we'll break them down. What are the components that we have? We look at the first one, v1y, which is just actually v1. There's nothing for the second one. And then the third one here is v3y. We already have v1y because it's just the value of v1, but we do need to calculate v3y. So we can just write v1y is equal to 3 newtons. And V3y is going to be 2 sine 30. So that same idea. It's sine 30 is equal to the opposite over hypotenuse. Then you multiply both sides by the denominator, which happens to be this side right over here, leaving you with, multiplying the denominator, which is 2, leaving you with 2 sine 30. So you get rid of it in the very similar way. So again, what does that look like if you were to do the slow way of just writing it out? Sine 30 degrees is equal to V3y over 2. Multiply this by 2, and what you end up getting is this right over here. This value over here, as we go about doing it, let's just double check. The first one, V1y, up, positive. This one here is down. This is going to be a negative value right here. So it's hard for me to show that. Maybe let's do that right over there. This is negative value. So whatever we calculate, it's going to be a negative value here. So sine 30 is 1/2. Well, 1/2 times 2 is just 1. So, but then apply the negative, you're going to get -1. So V3y is -1. Now we can add up V1 and V3. So V1 is 3, V1y that is, and V3y is -1. So we're going to have a value of 2 newtons. So our resultant vector, that's the final one here. So physics addition, vector addition is a little bit more complicated than your addition that you would normally partake in, which is fine. It's not complicated, it just takes a little bit of time to do. So at this stage, we have what our x component is, we have what our y component is. We just need to combine these two. And so that's +2, that's +6. So what I'm going to do is I'm going to start with my x component, and I'm going to just represent that with a value this way. Again, it does not need to be exactly like, say, 6.73 centimeters, where 1 centimeter equals 1 Newton. I'm just drawing an arbitrary amount to the right, because that positive represents to the right. 6.73 newtons. This is 2 newtons up. Here, I try to draw it to scale. So if this is approximately 7, then this would be approximately 2 or so, 2 newtons upwards. This is a right angle right over here. And then we're going to go from the starting point to the end point. So our resultant vector is going to be drawn like this. And this is our resultant vector. And we also need to make sure that we're going to be calculating theta right there as well. How we calculate our resultant vector is using Pythagorean's relationship. It's going to be a squared plus b squared equals c squared. And if you wanted to just write that in just above, that's fine. I don't require you to do that. I'm already going to skip one step where I'm going to square both sides. And I'm not going to be putting plus or minus because it's a positive length. So it's going to be the square root of these other two sides squared, 6.73 squared plus 2 squared. We're going to have a resultant vector of 7.0 newtons. And now we need to determine, well, what's this theta? And so if we look at our trig ratios, we have the opposite, we have the adjacent, we know these two values. That's going to use tan. So tan theta is equal to the opposite over adjacent. And in order to calculate theta, we're going to need to isolate the variable, the unknown. In order to swap these, we have to take the inverse. And so it's going to be the inverse tan of this ratio here, this fraction, is equal to our theta. And so that theta is going to be 17 degrees. So our final resultant vector would look like this then. This value here, 7.0 newtons. Followed by this angle right over here, 17 degrees. And if we look back to our diagram right here, it's north of east. So it was east, now it's going north. So it's 17 degrees north of east. Put it into these brick brackets. Underline our answer. And that is vector addition. So let's go through one more example here. So this one had some values going up, some going down. and then some going to the right. This next example here, we have one vector that's going east, and then we have one vector that's going 55 degrees north of west. So be aware there is going to be a negative value right over here. So let's do the same thing. Let's label these. We'll call this one V1, and we'll label this one as V2. This will be V2x, and it's going to be going in this direction over here. So be aware, this is going to be a negative value. It's going to the left, and then there's also V2y. This is a positive value. So this is going to be a positive value. That's going to be a positive value. This here is going to be a negative value. So just be aware that this is a negative value here. So let's start it off the same way as last time. Let's break it into the components. For us, let's work with the x components first again. So it's just going to be V1, and then if we take this over here, it's going to be minus whatever this vector is right over here, the 2x. We already know V1. And now for V2. And maybe this is better to be consistent like this. I've never done this before actually, but this might actually be smarter to like start it off this way, then you will never forget. Because as you noticed on this previous one, I forgot to kind of label these as positive right aways. And so it might just actually be more useful to do that. But if you find it better to do it later, then go for it. So our vector for 2x is again adjacent over hypotenuse, and so with this angle. So once we take the hypotenuse, multiply it on both sides, what we're going to have is value of, again, let's apply that negative right away, is 4 cos 55 degrees. Make sure your calculator is also in degrees when you're doing this, so that you actually get the correct answer. And let's just double check here. The V2x is going to give us negative 2.29. And see, so this is where it might get a tiny bit confusing if you say this is negative, like on this next line here, negative 2.29. Because the previous time there we had called one of them negative, but just called it V3y. So yeah, we need to maybe figure out just the consistency on that. Up until now, I've always just called this like positive, but recognizing that it is going to the left, it is going to be negative in the end. This is going to be negative. So it's going to be this positive 6 right over here, take away 2.29, or even adding negative 2.29. So 6 plus negative 2.29. Our total, and if you want to write complete total there, you could go ahead and write something like this, just Vx, I guess. Your total vector in the x component is going to be positive 3.71. The y component side. There is nothing in the first one, so we're only looking at the second one, and we're only looking at V2y, and V2y is positive, it's going up. So let's just go ahead and solve for V2y right away. That's going to be 4 sine 55 degrees. And again, if this doesn't track with you, just refer back to the first step first, where you write your trig function, angle, and then the ratio, and then just solve for the unknown value. You're going to end up getting this right over here on your second step. Your V2y will be 3.28. And now we will draw our resultant vector again. So start with our x value, 3.71, something to the right. This one here is almost the same, it's just a little bit less. So 3.28, 3.71. If you were to make a guess as to what this angle is, you should be hopefully guessing that it's a little bit less than 45 degrees in the end. Right angle, what's the theta, and what's the resultant vector. So we'll start by calculating our resultant vector. And so as you can see, this time I'm not going a squared plus b squared. I am just drawing this in right away. So I'm taking the square root of the square root of both sides there. We're going to get a value of 5.0 newtons. And this time, I will not be showing the previous step in the tan theta as well. So you see in that last example, I went tan theta equals this fraction over the next one. This time, I'm going to be skipping it directly to theta is equal to the inverse tan of this fraction right over here. So we'll start with that. Theta is equal to tan, because look at this, it's opposite over adjacent again. So the inverse of tan of the opposite, 3.28, over 3.71. And what we end up getting is a theta value of 41 degrees. And this again is going to be north of east. And you could kind of potentially make a guess as to what that looks like before too. How do we know it's more towards the right? Well, here we had 6 newtons to the right. This one had 4 newtons kind of up and to the left. So even if this 4 newtons had translated directly west, there wouldn't have been 4 newtons. There was only 3.28 newtons. And so it was definitely going east, and it was definitely going up. And so that's where your resultant vector is. So think it through as well. So when you're adding vectors, don't just blindly just add some stuff together, because you may forget these negative values, which is very, very important. You should actually think it through. When you go this plus this, what do you think is going to happen? And then when you calculate it out, did your thoughts actually match your calculations? And I would hope that the answer is yes, your thoughts did match your calculations. So in the end, we just have to say, well, what is our resultant vector? It's our value, the magnitude of the sum of the 2 vectors, as well as the angle at 41 degrees north of east. And so you have your magnitude, you have your units, you have your angle, and you have what is it in reference to. All need to be included when adding vectors. I believe that we will probably just stop there for today and get you working on assignments. So good luck and have fun.